Welcome back. Congrats on making it to Unit 2 of Integrated 3. Can't believe you're here. This is great. Lesson 1 is about logic. I hope you enjoyed that classwork. We're going to look at the Ready, Set, Go. Some of this is going to be a refresher of things you've already done, but we'll take a crack at some of them anyway. This has you graphing over the domain of -4, where it's less than or equal to x and less than, sorry, -4 less than or equal to x, less than or equal to 4. So this is going to be a little excessive what I'm about to do, but it might be something that makes your life easier. To plot some of these points, don't expect to see these on the other examples, but this might be an interesting way for you to take a crack at what's happening. So the work for all of these points we'll take a look at because we're being asked to graph this. We might be able to see some of these a little bit better than others, but we'll just go to town. So we'll start with 0, 2 to the 0 power, you guessed it, it's just 1. 2 to the first power is just 2. This is going to keep on multiplying by 2 as we go down, and also as we increase x by 1. So we could just keep that going here and to here and to here. So let's plot some of these. 0, 1, super simple. 1, 2, what you gonna do? 2, 4, get that point out the door. 3, 8, don't procrastinate. 4, 16, you can drive your car when you're 16. And then as this goes backwards, you could do this as division by 2, which again might be an approach that you take, getting you 1/2, 1/4, 1/8, and 1/16. So we're getting pretty low. So we'll use our best judgment here. 1/2 is between 0 and 1. Then we're doing half of that, half of that. You get the idea. It's getting pretty darn small. So if we do our best to sketch these out, not the best line. Maybe take a breather here, and then we'll take it to here, and then to here. Let me ask you real quick. Do you think we need to draw arrows on this graph? What you thinking? I would say no. I don't think you have to because the domain's restricted to just -4 for x and then 4 for x. So no need for arrows here. We're good to go there. What's up with the next one? Let's see. Do a little sketch. Let's do x. Let's do y. We'll start at 0 and then do 1, 2, 3, 4. And we'll probably see a pattern similar to before. So what's this work going to look like now? It always starts with 2, and then you keep multiplying by 2 to the 0 power, which is really just 2 times 1. And that's why here we're going to say that this is 2. And then here we're going to say that this is now 4, 8, 16, 30 dose. And those are a little different from before. Wouldn't you agree? How do you think that these new points are different? Do they start in a different fashion? Do they not quite multiply by 2? It's almost as if we have the same points, but they're just shifted a little bit, which can happen. I mean, this had 2 already working for it, so that's not the most obscure thing in the world. And we'll do our best to kind of graph this out and make it go smaller and smaller. Then graph that line accordingly. I believe that, and again, notice how this had a y-intercept of 1, but now it's 2. So there is a little bit of a shift as this continues. And to show that this keeps on going, I'll draw an arrow claiming that it's going to go to 432. There you go. You'll do something similar with problem 3. And is that really all that's it? Yeah. And you'll kind of compare and contrast what's different. I mean, compare problem 1 and problem 2. Multiplying by 2 should generate a vertical stretch of the graph, but the graph looks as if it was translated vertically. How do you explain that? What do you think? Well, it already starts with 2, so it's starting with 2 for when you do 2 times 2 to the x instead of starting with 1. And I know that this isn't how the equation was written, but if you really think about that, 2 to the x, it's kind of saying, hey, there's like an imaginary 1 there that keeps multiplying by 2 however many times. So I guess that's one comparison you could explain, is that 1 has a little bit more going for it already. So that's the ready. Hope that was cool for you. This is going to build off of what we have seen previously in Unit 1. We saw that if we have an exponential function, let's say it's f of x, what's that inverse function going to be? What kind of function is the inverse of an exponential function? Hopefully you're saying log. That'll come back again. So here we have f of x equals 3 to the x. F inverse of x should be equal to log base 3 of x. So we borrow this 3. We say it's our base. Pretty simple. Same song and dance here. Sometimes I'll use parentheses around x as the input. Sometimes I won't. Just be on the lookout for that. And I should note that these are vice versa. So if your normal function's log, inverse of that's going to be exponential. So that may help you with 10, maybe even 11. You do a little bit of a table work here. So it's claiming f inverse of 25 equals log 5, 25. And we see that should be 2, which totally makes sense, because if you think you have 25 equals 5 to some power, and this exponent's going to have to be 2 for this to be a true statement. So that's why here we're saying it's 2. Capiche? Makes sense? Take a moment, try 13, try 14. So again, more filling in the blanks. You're referencing the table. F inverse of 3,125. It's pretty much saying what's log base 5 of 3,125, which is 5, because recall, that's that. It's across the way. This one was a little tricky. It was now saying that your output was 1. So that means that you were taking this as your input, hence 5 here, and then hence 5 is your input for that inverse function. Capiche? Make sense? Pause, reflect, make sure it sounds okay. So for the next part, we're now looking at a graph. Before we had a table. It was pretty cool. I hope you would agree. We are working with what appears to be 2 to the x power. And this is for h of x equal to that. So we kind of do the same song and dance, but again, we're only given so much, so we have to think backwards. So if we're dealing with the inverse function of this, it's going to be a log, and that input's 1/2. So we have to think backwards here. We now are thinking if your output of y is 0.5 or 1/2, what's the matching x coordinate that goes with it? Well, and if you look closely, it's referencing this point here. If we put our attention towards the bottom, this output should be -1, which totally makes sense, because if you break this apart, you're thinking if you have 1/2 and on the other side it's a base of 2, notice base of 2, what's that exponent have to be? It's got to be -1. So that's how that one works. Take a moment, try 16, try 17, maybe try 18 if you're up for it, but definitely 16 and 17. Take a moment for that. So again, we're using the graph to reference which points are being talked about. Again, you're putting your attention first towards the y-axis here, and then thinking what point matches on that level. So get on their level, and then think out what the x-coordinate is. We talked about how 15 worked around this point, but 16 is referencing this point because your input's 1, and this is where on the graph the function is 1 for your outcome. So respectively, that happens at an x-coordinate of 0. And then for the quarter, 0.25, or 1/4. That's your thing. It's talking about this point here, and that maps out to being -2. Capiche? Makes sense. See you in the go. This is going to build off of a bunch of exponent rules that you've seen before. Anything to the 0 power is just 1. You remember that, right? You could treat this as if it's 11 times -6 to the 0 power. The -6 to the 0 power is just 1. So this is just 11 times 1. So your answer is 11. 11. This is subtracting 3 to the -2 power. So subtract, really, 1/3 squared, which if you take that further, you're subtracting 1/9. This is more desirable because we don't really want to keep negative exponents around. So this is just an equivalent way to write this. And we don't need an exponent because, yeah, that's what's even mentioned. Rewrite it so that it doesn't have exponents. We did just that. Cool negative exponent here. Pretty simple to take care of. 4 times 4 is 16. 4 times 16 is Nintendo 64. What a console. Incredible. There you go. 4 answers for that. And I believe the rest of the problems are similar. I'll knock out some of them. Hope that's okay with you. You could say that this is a negative exponent in your denominator, which is just no good. You should really treat that as if it's just 9 times 2, which is just 18. You could treat this because all of this in parentheses, I really don't care what this number is. I hope you don't either, or what it divides by here. The fact is that this all is going to the 0 power. So really, this is 3 times 1. So it's just 3. What'd you do? Compute this on your calculator? Silly. Similar to 23. 26 will be similar to that. This one's not too bad. 4 to the 3rd over 8 to the 0. 4 to the 3rd. 8 to the 0 is just 1. So really, it's just 4 to the 3rd power. This is just, you guessed it, 64. Capiche? Makes sense. Was this video helpful? Let me know. Hope you have a good day. Thanks for tuning in.